so we are dealing with randomized quicksort. Okay, and today we will be completing the rest of the proof that we are targeting. That means the randomized quicksort in expectation. In expectation, its time complexity will be order of n log n. Okay, so that is our target, and we will be having this target fulfilled today. Okay, so we have got the preliminary setup that how to analyze this. Okay, we are taking that, okay, if the kth smallest element is chosen as the pivot, then what could be the structure of the recursion, okay, or the recurrence, and we are taking all possible combination. Okay, so all possible combination of that random variable Tn, and then we are taking its expectation. So that is the overall idea of our next subsequent proceedings. Okay, and we have seen that, okay, whenever we are choosing, say, n elements are there and kth smallest element to be chosen, that means any one of these n elements could be chosen as the pivot. Okay, so it is equally likely that anybody can be picked up as the pivot. Anybody means any element, right? So if kth smallest element is chosen as the pivot, then the recurrence that we had was this. Any element is chosen as the pivot, then this was the recurrence. Okay, I mean this kth smallest element. So k minus 1 elements will be there in the left hand side, tn minus k elements will be in the right hand side, say, and theta n will be, we are having, bulk of the time is for this divide and conquer. That means this partitioning will be taking bulk of the amount. Okay, so that is theta n, right? So this is the recurrence, and with this indicator random variable xk, that means when kth smallest element is chosen as the pivot, then it will be 1, otherwise it will be 0. So this all possible combination we can capture with this by multiplying this indicator random variable with this random variable. Okay, if I put k equals to 1, then the first smallest element is chosen as the pivot, then x1 will be 1, and then this will be the recurrence. Okay, if I put the value, it will be t0 plus tn minus 1 plus theta. Likewise, it will be for k equals to 2, k equals to up to n. Okay, so you have got this tn. So tn is, we have got this xk indicator random variable which is capturing the all cases, and this is tk minus 1 plus tn minus k plus theta n. Okay, and then this will be summed up with all possible cases of k equals to 1 to n. So this is the equation we have got. Okay, and we are dealing with expected analysis. So we have to take expectation both sides. So expectation both sides we have to take, and this expectation both sides we are taking. Okay. And then what we have seen by linearity of expectation, this expectation should be inside. Okay, so this expectation we have to take inside the summation. So this is by the addition property. We are taking expectation inside first. So this is xk, and this term. This term I am not writing, it's say something dot. Okay, xk times this term, all these terms. Okay, right. And what we have got that, okay, this xk and whatever random variable we are having here, these two are independent. Okay, And then if these two are independent, then multiplicative rule we can apply this xy. So it will be expectation of x times expectation of y. Okay. So with this formula, we can separate these two right now. So it will be, now it is inside this k equals to 1 to n with this multiplicative rule. Okay. We are having, it is expectation of xk times expectation of this whatever. Okay. So this dot means this, all these terms we are not writing because it is time consuming to write all these terms. Okay. And what is this expectation of xk? Who will be telling? Expectation of xk, xk is the indicator random variable. Then 1 by t, k. Why it is 1 by k? 1 by n. Okay. Xk is the indicator random variable, and this k is chosen as the k smallest element is chosen as the pivot. So that particular element will be chosen as the pivot. It is equally likely we are having n elements there in the list. Okay. So this expectation of xk, it is probability of that event happening by lemma that one. Okay. So it will be 1 by n, and this 1 by n is not dependent on this k. So I am taking 1 by n outside, right? 1 by n. And that inside k equals to 1 to n. Now this expectation, I am writing this right now because we need to write this right now. This t n minus k plus theta n. Okay. So slowly and gradually all these things are getting simplified. Okay. Right. So I'm moving slowly so that you can comprehend all these steps, what I am deducing, right? Okay. So now this what I can do. So this is these are all random variables, or including all these. This is the combination is also a random variable. Okay. Two random variables whenever I am adding. So you can think of this the whole thing. If I am thinking as a whole, then it is also a random variable. Okay. So this I can think of that this is expectation of this random variable, this plus something. This theta n. This is not. This is theta n. This is not the random variable. This is theta n. Okay. So it is this t, we have defined this tn is the random variable. Okay. Right. So this is the random variable, this is the random variable, and we can think of this is not dependent on k. Okay. So this theta n is not the random variable. This is, we can think of, perceived as a constant here. Okay. So what we can do is, by linearity of expectation, again this is expectation of, say, t k minus 1 is x, t n minus k is y, plus this some constant c. Okay. So if I am taking the expectation like this way, say this t k minus 1 plus t n minus k, okay, taking these two as a random variable. I am taking this term as x plus some c, okay, plus expectation of this theta n. And this is k equals to 1 to n. So this we have got. So this is the whole thing is multiplied by, this whole thing is multiplied by 1 by n again. Okay, right. So now what we can, so here we have done this up till this part, this much, up till this much we have done here. Now what we got to do is, we have to multiply this 1 by n to this term, and then we have to multiply here. We have to multiply this 1 by n with this k equals to 1 to n theta n. Okay. So that I am separating it out right now. So this is 1 by n, and this term I am not writing as a whole, k equals to 1 to n. This term, expectation of some, say, dot. Okay. So this term I am dissociating first. This term will be treated separately. Let us simplify this portion because this is easy case. This is not random variable. So this is this, and this is k equals to 1 to n, expectation of this theta n. Right? So now this term I am denoting as something say, okay. This term will be taking separately, okay, plus this 1 by n. So expectation of some constant is that constant itself, okay. So k equals to 1 to n, this is theta n. Okay. So expectation of this theta n, as this is not random variable, so it will be theta n itself, okay, by definition. So now this k equals to 1 to n theta n, okay. So how many times I am multiplying that theta n? So what will be if I am simplifying this, omitting this summation, then it will be what? N times theta n, and divided by this n. So it will be theta n. So it is becoming a plus this theta n. Okay. So this is what we have written over here. Okay. So this thing is a, and this is our theta n. Okay. So this much we have got. We are simplifying it slowly and gradually. Okay. Right. So we had big expressions, so t k minus 1, t n minus k, theta n inside all summations, okay. Slowly and gradually we are simplifying these things, okay. So now this, okay. Now some observation you got to notice that this is the A, that means this part, okay. This part, whole part. This whole part is this A. Now if you put here k equals to 1, if you put here k equals to 1, then it will be what? So inside the expectation, this tk minus 1 will be t0 plus tn minus 1. Are you getting? If I put k equals to 1, then what expectation we have to find out? Expectation of tk minus 1 means 1 minus 1 plus t n minus k means n minus 1, k is 1, plus, this is. So this is, I am taking inside this expectation term, tk minus 1 plus tn minus k. So it will be t0, 1 minus 1 t0 plus tn minus 1. Are you getting? If I put k equals to n, then what will be the situation? So it will be t n k minus 1, that means t what will be this? Can you tell me? Tn minus 1, instead of k I am putting n, okay? And n minus k, what will be that? T0, okay? So you see, if I put k equals to 1, it is becoming T0 plus Tn minus 1. If I put k equals to 1, it is becoming T0 plus Tn minus 1. Now, if I put k equals to 2 or k equals to 2, then what it will be? It will be T1 plus Tn minus 2. Okay. Are you getting? Inside, everybody is with me? That inside formula I am putting here, k minus 1. So k, this is inside summation. So I am trying to separate, or I am trying to unfold this summation. Okay. So t k minus 1, whenever I am putting 1, then some structure I am having. If it is n, then I am having the same structure. If I am having k equals to 2, then I am having T1 plus Tn minus 2. Then if I am putting k equals to n minus 1, then Tn minus 2 T1. That means the same thing I am getting. Are you getting? Okay. So then T3 and T3 and Tn minus 2. That means k equals to 3, k equals to n minus 2. If I am putting, then same structure will be having. Okay. Right. So if that is the thing happening, okay, then you see for a particular k equals to 1, I am getting two terms, T0 and Tn minus 1. For t equals to n, I am getting two terms. So for particular k, I am getting two terms, right? Now what we can say, we can infer from this that for k equals to 1 to n, we have that each term appearing twice, isn't it? Each term appearing twice. So for k equals to 1, T0 is coming. For k equals to n, at the extreme end, then T0 is again coming. Okay, so T0 will be coming twice, right? Similarly, T1 will be coming twice. T2 will be coming twice. Likewise, we are observing that for k equals to 1 to n, each term appearing twice. Okay. So what we can say right now, this expectation of Tn. So this is you see, this expectation of Tn is going on and on. Okay. Right. So what we can say here, this expectation of Tn became that a plus theta n. A means this. And now this term I am again simplifying. Okay. And this I have got that, okay, this is, we can write this is 2 times 1 by n. 1 by n, I can write like this. 1 by n is there and each term appearing twice. So 2 I am taking common and I am taking outside. Okay. Then I am getting inside what the term k equals to 0 to n minus 1, expectation of this tk. And this is one term, this is our a, and this plus theta n. Theta n is outside this summation. Okay. Can I write this? So now if I unfold this summation, then what it is coming, k equals to 0, it is expectation of T0. Okay. Right. It is expectation of T0. k equals to 1, it is expectation of t1, right? And n minus 1, it will be expectation of tn minus 1. So remember that this, whenever k equals to 1, the term which is appearing is t0 and tn minus 1. So now the previous summation was from 1 to n. Now this summation will start from 0 to n minus 1, because whenever I am putting that k equals to 1, it is starting from t0 and it is ending with n minus 1. We are now sandwiched between 0 to n minus 1. Previously it was 1 to n. Okay. Whenever I am unfolding that summation, we are getting a cryptic notation, but the summation starting from 0. Okay. Are you getting? Huh? And this expectation of t0, this is appearing twice. Okay. So it is 2 times this plus 2 times expectation of t1 and so on. Then 2 I am taking common. Okay, so 2 is outside, right? So it is, that's why it is written 2 by n. And this is summation k equals to 0 to n minus 1, expectation of tk. Hello, are you listening? You? Huh? Listening? So you see, we had a big expression. We had a very big expression like this. And now, after several algebraic operations, we have got a very small cryptic notation. Okay? Right. So this is how the simplification goes on. And if we understand each and every step, then it is a fun. From the childhood, you have learned that all of you are very much fond of mathematics. From the childhood, that's why you are here. But coming here, always you are in celebration mode. You are always celebrating something. Dead at night, 3 or 3:30, we are roaming around and we are seeing. You are not being giving any chance to sleep. You are not giving any chance to us to sleep. We are having family, right? Okay. It is not possible. We have to take some kind of decision. But coming here, always you are in celebration mode. Okay, so that's why you forget everything. You think math is absolutely horrible. Okay. And it is not required at all. Okay. So now this we have got this. We have got this. Okay. Right. So now we have to prove that this expectation of Tn. So you see, whenever I am having, say, Tn equals to 2t n by 2 plus some kind of theta n like this. Okay. So this is in here and n by 2 here. Okay. Now you see here, even if it is inside this expectation, but the structure is almost the same. It is n here and it is in terms of k. K may be less than or equal to n. Okay. So here this is some kind of k which is less than or equal to n. Okay. Right. So this structure and this structure is almost similar. So we can think of that, okay, the treatment we gave for the substitution method to prove for this recurrence, we can give it for this also, which is this recurrence inside this expectation. Okay. we are proving this expectation of Tn with the recurrence, with the substitution method of proving of getting result for recurrences. So let us suppose expectation of Tn, we targeted that this expectation of Tn should be order of n log n. So let us suppose that this is order of n log n. So this is the guess. Okay. This is the guess we have got. Whether this case is correct or not, that we got to check. Okay? Right. So this we have got this case, and if we don't get that this guess is correct, then maybe we'll be having our face like this. Okay. So let us have this smiling face on. Okay. So this expectation of Tn, we have got this order of n log. This we have guessed that, suppose that this is the solution. Okay. Then this what we got to prove? We got to prove that this expectation of Tn is less equal to dn log. Now inside this summation, okay. So this so inside this it is expectation of Tk. Now what we got to do in this substitution method? We have to assume that it is true for lesser values of n. Okay. So it is lesser value, that means it is true for k. So this expectation of Tk, it is true for expectation of Tk. If it is, then we can write that expectation of this Tk is less equal to d, instead of n we have to put k log k. So this value we have got. We have assumed that this is true for some Tk. This is the proof of substitution method. Okay. We have to assume that it is true for some lower values of k. So now this expectation of Tn, what it is coming? It is less equal to this. We are putting this here. We are putting expectation of Tk value. Expectation of Tk is less equal to dk log k. So it is less equal to, term is coming here. Less equal to. So it is 2 by n summation k equals to 0 to n minus 1 dk log k. And this theta n I am representing it's by its upper bound Cn. We have got a constant d over here, so we have to take another constant here, Cn. So now you see inside the summation, whatever we have to manipulate, that is free from expectation. Now you know, means okay, you are a little bit comfortable, you are a little bit in a comfortable zone. Okay, you are having some comfort zone here, right? And you can think of that how to manipulate this thing, right? Okay. So you have got that expectation of Tn is less equal to this, and then this d is not dependent on k, so I am taking d outside, 2d by n, and this k equals to 1 to n minus 1 k log k. And this is the term, it's still little bit annoying. Okay. We have to, other things are okay, we have got its result, but this summation k equals to 1 to n minus k log k. So it was k equal to 0 to n minus 1 dk log k, and now I am writing k equals to 1 to n minus 1. Is it okay? Why? So the first term is automatically 0. So we have omitted that thing, right? Huh? So if I put k equals to 0, it is 0. So there is no point retaining that thing. So that's why if I write k equals to 1 to n minus 1, it is absolutely fine, right? So it is k log k, and so this term to be bounded. And if I can bound this, so we can bound this expression, right? So now this term we will be bounding by taking algebraic manipulation as well as with the help of integration. Okay. So this is the formula that this k equals to m to n fk. Okay, so this we can approximate with this integration. This is m to n plus 1 fx dx. Okay. This summation. So integration means nothing but summation, some kind of summation. Okay. So this term, whenever this term is introduced, the life became miserable. Okay. So this is nothing but the summation term. Right. If that term could have been like this, it could be good, I guess. Anyway, so whenever this term is coming, I get confused. Okay. But this term is very much, I am in a very comfort zone to go with this. Anyway, I have to be in some confused state with this integration sign right now. So this is m to n plus 1. This is a formula I am just putting. Okay. So this is there in appendix of Corman, and in any mathematics textbook you will be having this. Okay. This formula, uh, they are proving this formula by taking that whenever we take this integration first time, we approximate the area under the curve with this smaller rectangles. Okay, the rectangles will be smaller and smaller again, the better will be the approximation. Okay. Right. So with that thing we can prove this thing, but we are not going to the proof because it will be a little bit digressing at that time. Okay. So now we have got this, and in our example we have got k equals to 1 to n minus 1 k log k. So this is our fk. Okay. Summation, this k log k is now fk. Okay. Fk, k log k. So this is of this form, summation k equals to m to n minus 1 fk. So that will be approximating by this integration. So m equals to 1 here, and this is n plus 1. N is n minus 1 plus 1. So this is n. Okay. Are you with me? This is simple. Okay. Integration 1 to n, right? And this is fx, that means x log x dx, right? So this thing we have to manipulate. Okay. So you try to manipulate this in your hostel. We can complete this manipulation in the next class. Okay. Any question?